everybody. I'm going to talk about V8. So this talk is going to be about JavaScript, but basically JavaScript from the other end of your stack. So far we have been looking at JavaScript from the top of the Node.js stack. Now we're going to look at it from the bottom. So I'm a software engineer at Google. Basically I'm a VM and compiler guy, and we love to have assembler in our slides, but I try to resist the urge, so there is no assembler in my slides, I promise you. Okay, let's get started. So I heard you like speed, right? That's awesome, because that's one of the main design goals of V8. Be the fastest engine out there for some definition of fast. And that's one thing we know to be true, so being fast is always better. But how can you be fast? One way is to put hard work, to put effort into it, and after some time it might pay off. But actually we are all lazy, and we know laziness pays off right now. And that's kind of our philosophy on the V8 team, and I'll try to explain that a little bit more by examples. So here is a recipe how we think JavaScript virtual machines can be made fast. One ingredient would be inline caching. So when we are accessing properties of an object, at the moment when we first compile the code, we don't know how those objects will look like. We don't know the layout yet. We could invest a lot of hard work to figure that out right away, do it right on the spot, but we could also be lazy and just put an inline cache in there that patches itself once we know how the object looks like. So basically procrastinate that work and do it later. And that's what we do. We put inline caches that are uninitialized into the code that we generate right away, be done with it, and once we know how the objects look like, patch it and make it faster after the fact. Second example would be Crankshaft, the optimizing compiler. Many people think the best idea would be to just optimize everything, but that's actually not true, because compiling a highly optimized function from JavaScript takes a lot of time, a lot of effort. And again, we are lazy. We only want to invest that time if it really pays off. And we can figure out if it pays off after a certain amount of time. So we procrastinate, wait a little bit, observe your application, and once we figure out what the hot methods are, we optimize those. A third example would be the garbage collector. We have a new incremental low-pause garbage collector. Since incremental low-pause garbage collector doesn't sound flashy, we just call it new GC. That's flashier. And that third part is actually what the first part of my talk is about, the garbage collection. So we're going to look at how garbage collection works in V8. So garbage collection is all about dead objects, right? By raise of hands, who thinks garbage collection deals solely with dead objects? Nobody, really? Okay. You're right. Garbage collection isn't actually about dead objects, it's about live objects, and here is why. The full garbage collector, so the thing that does the heavy lifting of garbage collection, the real power horse, is a mark and sweep garbage collector. So as the name suggests, we have two phases, marking and sweeping. And marking is basically the process of finding out what is alive in the heap. So we start from a root set and basically follow the graph that your objects build in the heap and mark everything that we can reach from there. And that clearly is proportional to the number of live objects. That has nothing to do with dead objects. Everything that's flying around in the heap that we can't reach doesn't matter. Second part, sweeping. That's all about dead objects, right? Actually not really. So sweeping looks at the gaps between live objects. It doesn't matter if this gap contains 100 dead objects or just one. We don't care. We don't look at dead objects anymore. They don't matter to us. So sweeping also only depends on the gaps between live objects. Again, not really proportional to dead objects. And by the way, mutator is just GC lingo for your application. We call it mutator because it constantly messes up the heap that we try to clean up. So it mutates everything. That's why we call it mutator. This mark and sweep looks like a big pause. It introduces a potentially big atomic pause. And that's kind of not in line with Node.js's non-blocking architecture. So that might cause a problem, and that also caused some horror stories in the years ago when people said, "Oh, my Node.js application pauses for several seconds," and you're right, that's a problem. So how can we fix that? Well, one idea is just to chop the marking work into pieces and interleave it with the mutator work. So make it look something like this. And that's completely in line with Node.js's architecture, I guess. Do small amounts of work and then move on to the next thing. Yeah, sounds easy, right? Why didn't we do it right away? Well, I mean, that's a good idea to have, but implementing that isn't that straightforward as it might look on this graphic. So let me explain that a little bit. Garbage collection is all about painting the world in two colors, black and white. White is everything that's dead, not interesting to us. Black is everything that we can reach, that's alive. That's the interesting part. So basically, that's all that marking does, distinguishing between dead and alive objects. But as in real world, not everything is black and white. There is gray in between. And for a garbage collector, gray basically means this object is gonna be black, but we didn't actually look at it yet. So if you think about the graph traversal that the marking step of the garbage collector does, it has to find out whether an object is reachable. And if that object is reachable, look at its content, scan through it to continue its graph traversal. And gray is exactly the step in between. We reached the object, but we didn't look at it yet. And since we want to interleave the marking steps with the mutator steps, we need to keep track of this color. We need to keep track of objects that are going to be alive, but that we didn't scan through yet. And now let's look at different pointers that objects can have. If you have a pointer from a black to black object, perfect. That just means you have two live objects, they point to each other, we already reached them, we will not kill them. Black to gray, also fine. Gray is gonna be live, we just didn't look at it yet, but a pointer from black to gray is okay. A pointer from black to white, on the other hand, that can never happen, that shouldn't happen, because that means we looked at all the content of the black object, looked at all its pointers, and suddenly there's a pointer in there which points to a white object. So that's not marked for scanning yet. So this situation can never happen. If we wouldn't interleave the marking steps with mutator steps, we would just make sure that that never happens. But since the mutator can mess up the heap, it can create such a situation. And we must prevent that. And that's the tricky part about it. So let's look at it. Let's look at an example. So at first, the mutator creates a graph. Bunch of objects lying around on the heap. They're somehow connected. We don't know about the actual structure of the objects, about the actual structure of the graph, but we're gonna start scanning it. So the GC starts with its first marking step. So it starts with some root set, indicated by the leftmost arrow, and it's gonna scan through a couple of objects, and at a certain point decide to stop, to let the mutator continue. So we have successfully scanned two objects and marked two objects to be scanned. And now we're gonna stop and let the mutator continue. And now the mutator comes along and messes up our perfectly marked heap. So the object A is changed, and a pointer is changed. It no longer points to a gray object, but to a white object. So let me animate that for you. And that's where the write barrier kicks in. That's the WB. So the write barrier makes sure that the marking invariant is preserved, that there are only gray objects pointing to white ones, not black to white. And that means we are going to look at object A again. We're going to scan it again. Now the second marking step is going to kick in. And this time we're going to finish the marking. So we built the whole transitive closure of your graph, and we've visited everything that's reachable. Sweeping will make sure that the gaps in between can be used for further allocation, and everything that was marked is going to be preserved. Now, if you look at those two objects, you see that they are actually no longer reachable, so they should be considered dead, but they aren't, because of this whole marking invariant write barrier thingy that we discussed. But that doesn't actually matter, because those objects will survive another cycle, but will be collected in the next cycle. That's another example of where we are just lazy. We just let those objects survive another cycle and deal with them next time. So that's basically how we can achieve incremental marking, so interleaving the marking steps with the mutator. We can do the same thing with the sweeper. That's called lazy sweeping, but I won't go into the details of that. Let's just say that can also be chopped up into pieces and interleaved with mutator steps. And with this design, we reduced the pauses, the maximum pause that was an atomic pause before, and made sure that we only have incremental pauses. So the observed behavior of the application is a smooth behavior. So why did I tell you all of this? Well, for one, I think it's pretty damn interesting, or for the Irish folks, bloody interesting. But the most important thing is it exemplifies how we may be sacrificing some space for the sake of speed and responsiveness. Definitely responsiveness in this scenario. So there is this implicit trade-off between space, memory consumption on the one hand, and speed responsiveness on the other hand. And we chose this trade-off to be the right thing in our minds. Now, there is not much you can do about that except write your own GC, but it shows that being lazy might pay off and might lead to a steady progress instead of a progress that's pickled with pauses. And now on to the next part of the talk where you can actually make a difference, where you can actually change how V8 behaves. So finally, let's look at some JavaScript code. This is the famous point example. Most of you might have seen it already, but please stick with me. I'm trying to giving it another spin. So so far we have looked at objects being just those pebbles. They all look the same, they had no structure, but that's actually not how objects look like in memory. They have properties, they have different sizes. So how do we actually come up with the object layout? And that's what this example is about. Objects in JavaScript are actually just dictionaries. And we have one representation that represents objects as dictionaries. If they are in that mode, they are in the dictionary mode. But dictionary mode is basically just short for slow performance, so we're not going to look at that. Let's look at the most performant object representation that we have, and those are in-object fields. So when you first execute this constructor, you create a new object, an empty object, that has a hidden class associated with it. That hidden class describes the layout of the object so that we can remember where we put stuff. And as you can see, we leave some slack. So we have some space in the object. We over-allocated it. We don't know how big the object will be, because that's, again, hard to find out at that time, and we are lazy. So let's postpone this decision a little bit. Now we add the first property. We see if we still have slack in the object. Perfect, there still is space, so we put it in the first in-object field. And that's really a field directly in the object, so there is no indirection in between, no dictionary hash table thingy going on. It's really just an object, and inside the object is the value for x. Same thing for y. We still have space, we can add it to the object, and on the right-hand side, you see we keep track of the object layout through our hidden classes. So when we do the same operations on an object again, we follow the same hidden classes, and the types that we gather are monomorphic. So do that again, a second object, and now comes this crazy part which modifies the object after the fact. So for some objects, we add a third field to it, the set field. And this still works fine. We still have space in the object, so we just add it as another field. But now the object has gone, or now accesses to those two objects will go polymorphic, because you actually have two different types of objects. One that contains x and y, and another one that contains x, y, and z. So not really a good place to be. Polymorphic is always is worse than monomorphic. You want to be monomorphic when it comes to speed. So we'll continue doing that, create a bunch of objects, and at some point V8 decides to freeze the layout of the object. So we have seen enough objects, we have seen what your application does. Let's actually get rid of the slack that we have in the object. So we have over-allocated objects. There are 4 words in size. That's too much. We can shrink it. So we shrink all those objects, and the next time we create them with the right size. So we shrink all of them to size 3. But actually, that's not true for all of them, because some of them only have 2 properties. So you actually waste some space in half of the objects. So you just got the worst of both worlds. You're slow because you're polymorphic, and you waste some memory. So let's fix that. If you're looking for speed, you should just make all of those objects look the same. So have all of those objects x, y, and z properties, and just leave the z property to 0, undefined, whatever. If you're looking for reducing your memory footprint, you might want to still be polymorphic, so have 2 classes of objects, but you don't want to have that waste. So what you should do here is actually make sure that you have 2 classes of objects, one which has just 2 properties and one which has 3 properties. And with this structure, V8 can actually figure that out. So here you are polymorphic, but at least you're not wasting memory. So just to show that actually makes a difference, here is the difference for a ray tracer application where I saw this pattern and hacked it into it. And you could potentially, in a real-world application, achieve a difference of around 40% of memory consumption with that. So if all of that doesn't interest you at all, you should at least take away some best practices, or think about what I just told you and be sure to only break these best practices if you know what you're doing. So one thing, try to initialize all properties in the constructor. That helps V8 immensely to figure out how objects actually look like in memory. Add properties in the same order, so that we can keep an sane hierarchy of hidden classes, and avoid object layout modifications after the fact. So all of this only matters if you're dealing with hot objects. That means if you're either allocating lots of them or using them in a hot function. Now, because I'm running out of time, let me just go through the second example really quickly. The same basically applies to arrays. So for arrays, we also allocate an array, leave some slack in the actual backing store. So here again, we over-allocate the backing store, and then we start adding to those to this backing store when we add elements to the array. So We add 23, everything's working fine. We can store integers into the backing store, same for 42. But now we're adding a double. So that backing store cannot handle doubles. We have to transition away. We have to change the backing store so that it can store doubles, make the backing store bigger, so that it contains 64-bit words. That means we have to allocate a new backing store and convert all the elements that have been in there before. And now we add an object. Ah, damn, we screwed up. We have to go back to the 32-bit representation to be able to store the pointer to the true value, convert the 23 and 42 back again into an integer representation, and box the double into a 64-bit box. So if we do that a couple of times, we end up with all of the backing stores looking the same. That cost a lot of work. The allocation doesn't matter that much, but the transitioning of the backing stores back and forth between different representations, that's costly. And also, it kind of seems wasteful that we have several backing stores all holding the same values. So that's just all screwed up. Let's fix that. How can we fix that? Well, for example, we could just use an array literal to represent that. And array literals are great. We can figure out ahead of time how many elements are in there. We can determine what the type of the backing store should look like. And the greatest thing about that is we can actually make it copy on write. And that's again another example where we are lazy. We just allocate one backing store that holds the initial values and use that for all the arrays you create with that literal. And only if you actually write to that array and change one of the elements, we will copy the backing store and then write to the newly copied backing store. So that's what the COW means, copy on write. And that's again another optimization that saves potentially a lot of memory. Yeah, again, best practices. Feel free to break them if you know what you're doing. Try to initialize all arrays using, all small arrays using array literals. Array literals are just awesome for a VM. Pre-allocate arrays to the same, to the correct size, again, for small arrays. And try to use arrays to store one kind of value in them. Don't mix true, undefined numbers, doubles, whatever. And with that, you know how, or you got a glimpse what the engine in your vehicle looks like, and hopefully that allows you to drive safe. That's all I have for you. Thanks.